The day started like any other in the cold, empty void. Nothing but the quiet hum of cosmic background radiation and faint smell of ionized hydrogen. Then came a flash. A blinding burst of X-rays and gamma rays lit up the sector like a supernova's last scream. By the time the stellar dust settled, she was gone. Just a beautiful two-solar mass star torn apart in her prime. I hadn't even finished my morning coffee. Black, 2 sugars, hold the dark matter, before the calls started pouring in from every observatory in the quadrant. Another star murdered. I lit a cigarette, took a long drag, and stared out into the ink-black expanse. "All right, sweetheart," I muttered. "Who did this to you?" Her last known position was on the wrong side of the universe, smack in the middle of a dangerous neighborhood surrounded by 4 of the meanest, hungriest black holes this side of the event horizon. 1 in each quadrant, all of them staring, all of them with motive. I had questions, plenty of them. What was a nice main sequence star like her doing in a place like this? And more importantly, which one of these cosmic thugs finally crossed the line and ate her? Right, well, I hope you guys liked that awesome LA Noire style intro. The soundtrack is actually from the game LA Noire. But we're going to be looking at the gravitational force and how it interacts if we're just talking about gravitational bodies. So the premise of this problem is a star is surrounded by 4 supermassive black holes. Actually, these technically wouldn't be considered supermassive. They're just actually black holes. So I'm going to scroll down here to the less LA Noire style and just more of the diagram. This is really what we're going to be working with, okay? So it's a little hard to see, but you can kind of see right there in the middle. There's a star. I have it located for our terms of our quadrant and our axis. It's at the center. And it has a 2 right here, so I'll expand that. It's 2 with a little dot in the middle. This stands for solar masses. And so what a solar mass is, it's the mass of our sun. You'll notice right up here I have the unit conversion. Our sun is approximately 1.989 times 10 to the 30 kilograms. So we're talking about a lot of kilograms. So it's sometimes a little easier to say solar mass. So you can think this star is twice the size of our sun. That's how we would relate that. And these are our black holes on the whodunit. So for this kind of problem, we're going to be the detectives in figuring out who murdered or ate this star. And the way that it would eat the star is it would be gravitationally attracting the star. So the way we would solve this is to figure out what is the net gravity or net gravitational force acting on this star. The net force is going to be the direction that the star goes. Because it's magnitude with direction. So once we figure out its final direction, we can figure out to which black hole is it going to go to. So this is, if you're familiar with the unit circle and how we define quadrants on an XY axis, this is the first quadrant, this is the second quadrant, this is the third quadrant, and then this is the fourth quadrant. So that's how we're going to label our quadrants and orientation. The numbers on this axis are in astronomical units. An astronomical unit is defined as our median distance, the Earth to the sun, okay, which is approximately 1.46 or 496 times 10 to the 11 meters. So again, really big numbers, really big conversions. The idea here is to use our knowledge of forces and trig, because this is essentially a 2-dimensional problem, to get the net force acting on the star and figure out which direction it's going to go. So the below image is just of quadrant 1 blown up. It's just this quadrant expanded, so we can kind of see it a little better. So here's the star down here. It's got the 2 solar masses, and I've got the black hole A, which you'll see as 15 solar masses. So the black hole A is 15 times that of our sun. And it has a distance. This is its radial distance. We'll call RSA, or we could just call it RA since they're all to the sun, or all to the star technically, so that's a good way to do it. RA. That's going to be its radial distance. If I look at, or I remember the equation for gravitational force, Fg is equal to Newton's gravitational constant, the mass of the one thing, which in this case is going to be the star, the mass of the other thing, which this is the black hole A for this case, divided by their radial distance squared, which I'm calling RA squared. So I know all the masses. I know what Newton's gravitational constant is. What I don't know is what their radial distance is. In the equation, it's RA squared. We don't need to take the square root of this to solve it. It's actually nice that it's set up as RA squared. It'll simplify some of the math for us. So if you remember the Pythagorean theorem, for the sides of a triangle, a right triangle, the squared sum of the sides are equal to the square hypotenuse. So a squared plus b squared equals c squared. In this case, I have a right triangle. I have a hypotenuse, which is RA squared. That's what I want to know. That's equal to the two sides. Well, the x-directed side is 60 astronomical units, 60 AU. We'll put that in a squared. Plus the y-directed, the opposite side, is 30 astronomical units squared. And I can figure out RA squared as equal to 4,500, sorry, I can count, 4,500 astronomical units squared. Let's leave it in astronomical units squared. We will account for that in a second. Doing unit conversion at the end actually simplifies some things for us. But then I can go ahead and plug it into my gravitational force equation. So gravitational force, I'm going to call it FA to denote this is the gravitational force on the star from black hole A. That is going to equal the gravitational constant, the mass of the first star, which we know to be 2 solar masses, the mass of the black hole, which is 15 solar masses, all divided by the radial distance squared, which is 4,500 astronomical units squared. So in this case, then I get what is going to be 30. So I can do 2 times 15, which is going to give me 30 divided by the 4,500, and I get it is 0.0067. The units for this would be, I still have the gravitational constant I haven't derived yet. This would be solar mass squared over astronomical unit squared. Now, before we do the components, let me show you how we deal with the solar mass and the astronomical units. You'll see I have these conversions up here at the top. We're going to go and refresh our stoichiometry days, if you remember back in chemistry, to figure out how we can convert these. Before we do that, though, let's plug in actually G. So gravitational constant is 6.67 times 10 to the negative 11. This is Newton meters squared per kilogram squared. So I have meters here versus astronomical units. I have kilograms versus solar mass. So I need to convert those. So let's multiply G. I'm going to actually move this down. Let's move this down here because we're going to scroll down a little bit. We need some room to work. Let's multiply G to the whole equation. So my overall force is going to equal 0.0067 times 6.67 times 10 to the negative 11. You see we're going to get a small number to start here. It will counteract later. Trust me. This is Newton meters squared per kilogram squared. And then I'm just going to tack on the units at the end so we know that we have to convert them. So I plug this into my calculator and I get 4.45 times 10 to the negative 13. Having fun yet? The only reason this problem can be kind of tricky is all the numbers. But bear with me, it is kind of fun. We will figure out who done it. All right, this is going to be, I'm going to keep this unit all together, Newton meters squared per kilogram squared. And then this is still solar mass squared over astronomical unit squared. All right, so remember I talked about we're going to do a little bit of stoichiometry. So what I will set up now is what I call a railroad track. So I'm going to start with the number we know, 4.45 times 10 to the negative 13. Let's just keep this unit attached, 4 Newton meter squared, kilogram squared. Solar mass squared. Let's deal with solar masses, okay? And this is my railroad track. Let's have astronomical units squared at the bottom. So the way a railroad track, or what I know it doesn't look like a railroad track, but my chemistry teacher is the one who told me that way back when I took chemistry, and it's just kind of always stuck. So you can think of these as two fractions next to each other. directly across is multiplication. Up and down is division, like you would see in a fraction. Diagonal is division. Down and across. So anything, yeah, just directly across is multiplication. Basically, everything else is division. But we can kind of set this up this way. The way I want to get rid of solar mass. So I have solar mass down here at the bottom. Technically, I want to get rid of solar mass squared. But I know one solar mass, so I'm going to go ahead and square that, is equal to 1.989 times 10 to the 30 kilograms. That also has to be squared. So when I have powers on the units I'm converting, I actually also have to square the values. Be careful of that. Same thing happens when you're converting area units also, by the way. 1 squared is just 1, so the solar mass is squared cancels. I'm going to be left with a kilogram squared, which you'll notice is going to cancel with this kilogram unit, which is what I want. So I'm looking for a force. The only thing I better have left is the newtons. So the way I would put this in your calculator, I would do the exponential first and then square it at the end, because it's not just increasing the 30 to 60, you also have to square this number too. So you got to be careful about order of operation here in your calculator. But this is going to be multiplied by, I would do like essentially 2 parentheses. 989 times 10 to the 30, square that. It's a big number, but we will also divide it by a number. It'll get a little smaller, but for now it's a big number. We have 1.759. Again, remembering these kilograms canceled. This is times 10 to the 48. This is now Newton meters squared per astronomical units squared. So we're going to do it one more time to get rid of the astronomical units. I'm going to start with 1.759 times 10 to the 48. Little did you know there was so much math involved in physics. Astronomical units squared. I want to get rid of astronomical units. I'm going to do the same thing here. So I want to get rid of it squared. For every 1 AU, right, we have 1.496 times 10 to the 11 meters. And that also needs to be squared. AUs are going to cancel. And you'll see my meters cancel, just leaving me with newtons. This will give me my end result finally in newtons, which is what I want. So I'm going to divide 2 parentheses again. 1.496 times 10 to the 11. Square that, close the parentheses. I get my final result as 7.86 times 10 to the 25 newtons. Having fun yet? Okay, so that's my overall force. But remember, with 2-dimensional problems, I have to break them down into 2 one-dimensional problems. So I can only add like terms to like. So in terms of the net forces, I can only add them if they're in the same direction. So I'm going to break it down into its horizontal and vertical component. The way I do that, the horizontal is going to be the cosine of the angle. The vertical is going to be the sine of the angle. Now we don't know what the angle is. So let's go ahead and figure out what the angle is. And I'm going to actually just do that right up here. I do know, though, that the tangent, if I remember SOHCAHTOA, TOA, opposite adjacent. The tangent of this angle is going to equal the opposite over the adjacent. Well, the opposite is the 30 AU. The adjacent is the 60 AU. Like the units will cancel. I'm left with 1/2. That's what the tangent of the angle equals. If we remember, how do I figure out the angle from that? I take the arc tangent, which undoes the tangent. So the angle theta is going to equal the arc tangent of 1/2. We can keep these in degrees. I get that the angle is about 26.6 degrees. Okay, that's what that angle is. So if I want to figure out what the x direction of this force is, and I can account for its direction, I know it's going in the positive x direction. It would pull it in the positive x direction. This is going to be the overall force times the cosine of this angle, 26.6 degrees. If I want to figure out the y direction, or the y component of the force, it's the overall force times the sine of the 26.6 degrees. And this is how we're going to be able to solve the rest of this problem, of which I don't actually fully solve for you. This is a homework problem that you guys are going to do that I want you to kind of work through. But this is how you set up the net forces for the first one. You're just going to kind of rinse and repeat this for the other three, and then add them all together at the end to figure out which direction it's going to go.